All right. So welcome to Authentication Demystified. As you can see from my title, I wrote this as a 60-minute session originally. We have 45 minutes, so I've slimmed down a little bit. We're going to get going and try to just get through all this fun stuff. So I am here because a few years ago, I made a huge rookie mistake. I was writing some code. I needed a piece of JavaScript to make an API call back to my server, and this server needed to know, who was making that API call. I didn't know how to give it that information. So I did a web search for how to authenticate an API call, and I found a pretty confusing mess. There were articles about federated identity systems and cryptographic hash functions and multiple versions of this thing called OAuth, and a whole bunch of acronyms and terminology that I didn't understand. It was all really daunting. I was in a hurry, so I cobbled together some code from Stack Overflow, and shocker, I shipped a security defect. Now, since then, I've learned a lot about authentication and authorization, so my goal today is to give you the coherent overview that I really needed back then. I'm going to break down all those complex terms and concepts into simple explanations so you can make an educated decision and not your own rookie mistake. Now, I want to be clear about what this is and is not. So I am not a security expert, and this is not an advanced security session. If you already know the difference between bearer tokens and signed requests, how JSON Web Tokens compare to OpenID Connect, and why OAuth should not be used for authentication, then this session really isn't for you. Additionally, in order to keep these concepts accessible to a wide audience, I've had to omit a few details here and there. Those details matter, just not to my core audience. So in other words, this is a great place to start. Don't go out and apply for an InfoSec job based only on this session. I'm not going to show you how to implement these techniques. There is stuff in this talk I have no direct hands-on experience with. I've never written any OAuth code myself, so I couldn't tell you how to add OAuth to your .NET Ruby application or whatever. But what I have done is I've Googled the crap out of OAuth. Or really, I've Googled the crap out of OAuth and how it works relative to everything else. And that's what this session is about. So here's the agenda. I'm going to explain these things at a high level so that you have a good mental model that you can apply to whatever getting started guide you go with. Now, before we get to that list, we need to define three main terms that will come up over and over. Let's say we have this website, and a request comes in for some URL, like foo42. The identity of that request is the person or entity that's making it. In this case, it's our lovely user Alice making the request from her desktop computer. Authentication is the process through which we determine the identity. It's whatever we do to make sure it really is Alice making the request. And authorization is the process of ensuring the identity is allowed to make the request. It's whatever business rules govern if Alice can access foo42. Now, when we're talking about authentication, we need some reliable way of verifying the client's claims about their identity. And the most common way of doing that is a password, right? You've all used them, you know how they work, but I want to very briefly discuss them because they demonstrate two fundamental concepts that you need to understand. So here's Alice logging into our website, and even though her password is masked out on the screen, it's submitted to the server in the form post as plain text. That means it goes out over the network as plain text. So if Alice is working from a public cafe, her credentials could be visible to any bad guys that are eavesdropping on that same Wi-Fi connection or any segment of the internet between her and us. If you use HTTPS on your login form, then the password gets encrypted by the TLS process, and as a result, it looks like gibberish as it goes over the network. The key thing about encryption is that it's reversible if you have the keys. That's kind of the whole point, right? It has to travel as gibberish over the network, but the web server on the other end has to be able to turn it back into text to validate it. So this reversible encryption was the first concept I wanted to illustrate with passwords. The second concept comes up when we talk about validating that form post on the server. So let's say that we stored Alice's password in our database as plain text. It'd be very easy to validate the login form because we would just query the database for the plain text values from the form post. Super easy. We're not providing what's called security at rest. That means that an attacker that gets access to the database gets access to all our passwords in plain text. Obviously bad. Now, we can increase security by storing the encrypted password in the database, not the plain text one. The encryption keys are stored elsewhere, so if an attacker were to capture the database, they only get the encrypted passwords. They can't reverse those into the actual strings. But for that to work, the web app would need to know the encryption keys so that it could encrypt the user-submitted password before searching for it. And if the web server is able to encrypt the password, then it can decrypt it as well. It can turn that encrypted string back into text. And if we have that ability, then we're vulnerable for that to be exploited. It may not be easy to steal the encryption keys, but if an attacker can do it, then again, they get access to our database, all our passwords at plain text. And it's just an unnecessary risk to do this because we have no legitimate need to ever decrypt someone's password. We need a way of ensuring they entered the right string, but we have no reason to ever determine the specific characters in that string. So a better approach is to use something called hashing. This is the second concept I wanted to illustrate with passwords. So hash functions are similar to encryption in that in both cases, you pass some sensitive string into a mathematical function, and you get some gibberish string as output. Now, the most important difference between them is that while encryption is reversible, hashing a value is a one-way trip, right? The hash cannot be reversed into its original string. Additionally, there are cryptographic hash functions that will convert every unique input to a single deterministic unique output. So no two passwords put through the same hashing function will generate the same result. Well, that's not quite accurate. I mean, technically it's possible that two different inputs will have the same hash output, but it is computationally infeasible to find those things in advance or to figure out which specific input led to a specific output. So while hash collisions are technically possible, we can generally ignore them when we're hashing values for security applications like I'm talking about here. Therefore, we can store a hash of the password in the user database, not the password itself. Since it's computationally infeasible to reverse the hash back into the original password, it's much harder to steal passwords at scale. Also, why we cannot email a user a copy of their password. Right? We don't have any way to actually get it, so all we can do is send an email with a link to reset it. All right, so that first example used a login form submitted by an end user. But what about computer-to-computer authentication, like when one of our integration partners wants to call one of our APIs? We can't use a login form because there's no human being there to interact with it. So the next simplest thing that you can do is called basic authentication. This is an internet standard for sending credentials in an HTTP header rather than the form post. Now, the name of this header is authorization, which is a little bit misleading. There are a few different ways of using this header, but when it's used like I'm describing here, it's all about authentication, not authorization. Now, the value of the authorization header consists of two pieces. The first is the scheme that tells us how to interpret whatever comes next. And for basic auth, what comes next is a base 64 encoded credential pair. And this is what that means. The client needs to know the password and username that it's using to authenticate with. It can get them from a config file, database, whatever. It has to have the information. It then concatenates those credentials together into a single text string, and then it base 64 encodes that string, which creates this thing that looks like gibberish. But it's important to note that that encoding isn't encryption and it's not hashing. So this value looks like gibberish, but this string can be turned back into the plain text password with no special key required. The point of the encoding is about making the piece of text easier to transmit across multiple computer systems. It has nothing to do with actually securing the value. That encoded string is then added to the authorization header and sent to the server. Server decodes the encoded string and then uses the credentials to authenticate the request. Now, the biggest drawback to using basic auth, like I just described it, is that it still requires knowledge of a password. And there's one big issue with using passwords for this kind of computer-to-computer API call. And namely, that's that passwords are the primary account credential. They are the key to the user's entire kingdom. So transmitting those credentials in what is basically plain text is a bad idea. Now, theoretically, using HTTPS would protect the credentials over the network, but what happens if someone forgets to use HTTPS, or if these things show up in a log somewhere where they're available to be decoded? So the point is, using the primary account password for API authentication is a bad idea. So a common alternative is to use API keys as a sort of limited privilege, usage-specific password. Let's say that our app integrates with multiple third-party applications. So instead of using her account password for those API calls, we could create separate API keys for each service. If someone hacks one of those keys, that's all they get access to, right? They can't use that credential to attack any other integration. And additionally, neither of those usage-specific credentials would allow someone to log into her account. Right? The keys are only used for the API calls, not logging in, changing passwords, etc. Now, there's no standard for what an API key looks like, so the naive solution is to use GUIDs. That's a mistake. GUIDs are designed for uniqueness. They are not designed for randomness, but randomness is what would make these things secure. If you use a standard GUID, the values it creates are too predictable for use in security applications. So most platforms do have some kind of secure UUID function that you can use instead. You just need to make sure that you use the right one. So once a key has been generated, there are 3 ways to use it for authentication. The first is to use basic auth, like we just talked about, but using the API key instead of the account password when you're creating that base64 encoded value. Another common approach is just to send the API key by itself in the HTTP header. Now, in this case, that key is being used for both identify the user and authenticate them, so those strings have to be unique and really hard to enumerate. And the third way of using API keys does not require setting them over the wire at all. This technique is called signing the request, and it uses the API key plus a hash function to create a cryptographic signature. This is how it works. The client still has to know some secret value. In this case, it's the API key. To make an authenticated call, the client prepares the URL that it wants to call with the parameters. It then concatenates that string with the user-specific API key. And that creates a string that's unique to this user's request for that specific URL. Any other user accessing the same URL will generate a different string because they will have their own API key. The client then runs that string through a hashing function, which creates a unique signature for the request. So the string being hashed is unique for Alice's request for that URL, and hash functions return a unique output for every unique input. So no other client will generate that signature unless it's using Alice's key to request that exact URL. The client then submits the request to the server, sending that signature in an HTTP header. Now you'll notice that the API key itself is not included in the request, so it cannot be stolen off the network. It was used to create the signature, but the hash value can't be reversed. So even if someone is eavesdropping, they can't extract the API key from any traffic they capture. Signing requests also protects them against man-in-the-middle attacks. So let's say this bad guy has infiltrated some part of the network between Alice and us. He wants to change one of those parameter values so that the server receives a different request than what the client sent. So a real-world example would be Alice trying to transfer money to a friend. If the bad guy can replace the friend's account number with his account number, he could trick the server into sending him the money instead. But if the requests are signed, then this man-in-the-middle attack won't work. Because when the server receives the request, the first thing it does is look up Alice's API key. It then uses its copy of her key to recompute that signature. If the signature that it calculated and the one sent from the client are different, the server knows that either the original request was signed with the wrong key or the request was modified in transit. And in either case, we can reject the request as invalid. Now, I glossed over one important detail. The whole process depends on the server using Alice's key to validate the signature. But there's nothing in the request that identifies Alice as the originator. So how does the server know to use her key for validation? So when you're using API keys to sign requests, your request needs to indicate the identity and the signature. Very similar to basic auth, which works the same way. So what should we use as that ID? Well, you could use some unique key from your database, like email address or user ID or whatever, and that works fine unless you want to allow people to create multiple API keys. If you support multiple API keys per user, and you only pass a user identifier in the header, then on every request, the server will have to loop through every key for that user until one validates. That's a lot of unnecessary overhead. So a common solution is to assign API keys an identifier of their own. Now that identifier is public and it is sent in the header as plain text. It is used only as the identifier to look up the corresponding API key, which we then use for verification. So this concept of using a secret key to hash some string and then sending the output as a signature is a major concept in authentication. The signature is an authentication code. It's created with a hash function, and that makes it a hash-based message authentication code, often abbreviated as HMAC. The thing that you should remember is that an HMAC algorithm provides message integrity, not message security. It allows Alice to send a message to Bob, and for Bob to confirm that the message he received was what she sent and was not modified in transit. HMAC does not secure the message itself, right? So make sure you send these things over HTTPS. That'll protect the message from eavesdropping and provide message integrity. Now, if a client and server have a shared key, that means the client has to store that key somewhere in between its requests. For server-to-server communication, this is easy, right? We generate a key, we put it in our database, a developer for the other application comes along, retrieves that key, and then preloads it on their client application. They can store it in a config file, database, whatever. Once that client app has the key, it can use that key to communicate with us. But what if the client isn't another server? It's one of those newfangled JavaScript front ends written in React. So Alice might drop by her local library on a Sunday afternoon, and she could log into our app from a public workstation. There's no way to preload her API key on that machine in advance. And without it, our React app can't make authenticator requests on her behalf. So we could have Alice sign in with her password, and we could send the API key back in the HTTP response, but there just isn't any way for her browser to store that key. That's because JavaScript is an insecure environment. Its crypto functions can be monkey-patched and replaced with compromised versions. Local storage can be attacked through cross-site scripting, etc. So the basic rule of thumb is that any data that you expose to your JavaScript can potentially be seen by someone else's JavaScript. So we cannot make the JS client aware of her API key without exposing that key to theft. So if we're working with a JavaScript front end, we need a different technique to handle authentication. And one solution to that problem is JSON Web Tokens, pronounced JOT. In a JOT scenario, the server has a private key that it keeps to itself. That key is never shared with any clients, and it's not user-specific. It is a system-specific key. Now, a user is still required to authenticate via some mechanism, like a login form. Web tokens don't replace the authentication step. They just provide a secure way of representing that the authentication has been conducted. So after the user is authenticated, the server constructs a JSON document of claims about that user. And claims are just pieces of data, right? The example here is a claim saying the user's username is Alice. The server then signs those claims using the same technique we saw earlier. But this time, the claims are being signed with the server's private key, not a user-specific key. And that creates a unique signature for the claims. A token is then created that contains the claims in plain text plus the signature. The same approach we saw when signing a request with HMAC. The token is then sent back to the client as part of the response, and the client browser sends it back to the server with all subsequent requests. The server can then validate the token by combining the claims from the token with its private key and then recomputing the signature. If the signatures match, the server knows that the token was signed by its own claim, or its own key originally, and wasn't modified in transit, so it can trust the values in the claims. In this case, it can successfully and safely authenticate the request as coming from Alice. But let's back up for a second. I just said that we couldn't use API keys with JS clients because JavaScript is insecure and cannot securely store the private key. Well, if JavaScript is insecure, how can it securely store the token in between requests? And the answer is that it can't. A JavaScript client cannot store a token any more securely than it could store a shared private or a secret key. If your JS code can access your token, then so can the bad guys. Anyone that can access the token can read the claims because they're stored in the token as plain text. But more importantly, anyone that can access the token can reuse it. In this case, because the token identifies the user as Alice, anyone that steals the token would be able to impersonate her in our system. So the solution is to not expose the token to JavaScript at all. Instead, store your authentication tokens in an HTTP-only secure cookie. The secure flag means it will only be sent on requests that are using HTTPS. That'll protect it from being stolen in transit. And the HTTP-only flag means the browser will prevent that cookie from being visible to JavaScript. That way, the authentication token cannot be stolen or inspected through script. Now, sometimes there's stuff in the token that your JavaScript app actually needs, right? Maybe you have user preferences or other things that your JS app needs to render the page. So in that case, just split your claims into two different tokens. Put the token with the authentication stuff into the secure cookie, then store the flags and the preferences and everything else in a token stored in local storage. That way, the authentication data is secure, but the JS app can still access the stuff it needs to render the page. Now, if the token is being used for authentication only, then it will contain a single claim telling us who is making the request. If we need to authorize the request, we'd have to run a query to get Alice's permissions and access level. But the cool thing about web tokens is that they can provide those permissions as additional claims. So if Alice tries to access something that requires like admin privileges, we don't have to query the database. We can just pass that authentication level in the token and get it from the claim. If you have a high volume API server, skipping those repetitive lookups could make a significant difference to the load on your server. Of course, using that cached data is all well and good until the data changes. If the token is properly signed, it will validate regardless of Alice's actual permissions. The validation just ensures the token was signed with the right key. It doesn't actually mean the data are valid. And this is what I got wrong a couple of years ago. I created a token that never expired. So once you got logged in, you were logged in forever. It didn't matter what happened to your account. You would just stay logged in. That's obviously very bad. So we need to limit how long this token is good for. So a simple solution is to add an expiration date to the token as an additional claim. On the server side, if a token validates but is expired, then you can log the user out and then reissue them a new and updated token when they log back in. But the challenge here is figuring out what that expiration period should be. If you expire the tokens too quickly, then you're going to annoy your users. You have to keep re-authenticating. But if you set the expiration too far in the future and an account gets compromised, you might not be able to respond very quickly. So a good balance between security, performance, and user experience is to use something called refresh tokens. So with this approach, you issue 2 tokens when the user logs in. The first is a short-lived access token that contains the user identity and their permissions. That token is only valid for a short period of time, but within that period of time, the server will just trust the claims without revalidating them with a database lookup. The second token is a longer-lived refresh token, and the only thing it contains are the user identity and a longer expiration date. So if the access token has expired, but the refresh token is still good, the client can pass the refresh token to an API endpoint and get a new updated access token. And to generate that new access token, the server would requery the database to get Alice's current data to make sure the new token is accurate and valid. So that allows you to regularly reauthorize the user, making sure that their credentials are still accurate without making them log in constantly. Another case for web tokens is single sign-on between multiple sites or applications. So let's say that you manage multiple web applications and they both have access to the same private key. Alice could log into server 1 and get a web token signed by that key. She could then go to server 2 and pass the same token. Since server 2 has access to the same private key, it can validate the token and trust it. It's called single sign-on because she signed on once and got a credential that gave her access to multiple systems. All right, so we're making good progress. Passwords, basic auth, and API keys are methods of authentication, or authenticating a user based on credentials they know. Web tokens are an example of a claims-based system that uses signed tokens to provide identity and permission information. The next thing I want to talk about is SAML. And the elevator pitch is this. It's an enterprise-grade version of JSON Web Tokens that uses XML rather than JSON. And actually, technically, SAML came first, so it's more accurate to say that Web Tokens are a stripped-down version of SAML. But in any case, even though XML is gross and outdated and all the cool kids are using JSON, SAML is still very widely used in enterprise single sign-on. In fact, the primary difference between them isn't that one uses JSON and one uses XML. It's that web tokens work best for single sign-on between systems owned by the same organization, while SAML is designed for cross-federation single sign-on. In other words, it provides a way for a company like Google to provide authentication and identity services to wholly unrelated third-party websites. Now, technically, it is possible to do cross-federation SSO with web tokens, but it requires adding a bunch of extra stuff into the mix. SAML was designed for that as a first-class use case. There are 3 parties in a SAML scenario. The first is the user that wants to do something, and we'll use Alice again. The second is the service provider. It's the website Alice wants to access. And the third party is the identity provider, which is the website that is responsible for authentication. So Alice first goes to the service provider, which she's not authenticated yet, so she's redirected over to the identity provider where she logs in. The identity provider confirms her identity with whatever technique they want. They then create a set of signed assertions containing her identity information. And in SAML, an assertion is very similar to a claim in a web token, right? It's a name-value pair. I mean, there are other differences too, but for this session, you can think of them as pretty much the same thing. So Alice's browser posts the assertions back to the service provider, who then validates the signature and uses the identity information to log her into their system. But now, if you're paying really close attention, you may have spotted a problem with that explanation. When I explained single sign-on with web tokens, both systems that she was logging into had access to the same private key, so they could both write and verify the claims. And that's great when you control both systems. But if you're integrating with a third-party identity provider, there might not be a shared secret key that you both know. So instead, SAML uses public key cryptography for signing and validation. And the idea behind public key crypto is that there are these key pairs that contain two mathematically linked keys, a public key and a private key. And these keys are special because there are cryptographic algorithms where a message that is signed with the private key can only be verified with the one and only corresponding public key. So the identity provider generates one of those key pairs, and it keeps the private key to itself, but it exposes the public key through a standardized SAML endpoint. That endpoint returns a payload that describes everything you would need to set up an SSO integration with that provider. So the service provider can then use that endpoint to retrieve the public key, which it then use to verify the assertions. This is similar to HMAC with one big difference. HMAC uses symmetric cryptography so that two parties have a shared secret key they both know. And that shared key means that either party can sign a message that can be verified by the other party, but they have to transmit that secret key between themselves in advance. Public key crypto is asymmetric because only one party knows the private key and can send the messages, but any number of other parties can get the public key and verify them. So one really nice use case for SAML is outsourcing multi-factor authentication. MFA can be a real pain to implement, and I want my team focused on our core competencies. So with SAML, we can push that authentication off to some third party, and they can implement whatever multi-layered security protocols we want to implement. All my app has to do is match the signed assertions to a user account in our system. All right, let's go on to OAuth, which also deals with a three-party scenario. So in this scenario, we still have our user Alice, and Alice wants to create holiday greeting cards using Shutterfly. But instead of uploading her photos all over again, she wants to use the photos she's already put into Facebook. So the question is, how do we secure the connection between Shutterfly and Facebook? Now, the simple approach would be for Alice to give her Facebook password to Shutterfly, but that would then give them access to her entire Facebook account, which is obviously a bad idea. OAuth solves this problem by creating a standard that lets Alice delegate authorization to access her Facebook data without sharing her password. So she has to authenticate first to Shutterfly using her Shutterfly account, and Shutterfly then makes an authorized request to get her data. And here's how it works. When Shutterfly wants to access her photos, they redirect her to Facebook. And that URL identifies the client, the type of access it's requesting, and where to return to after the access is granted. So Facebook authenticates Alice, asks if she wants to share her data. She says yes, she grants the access, and Facebook responds with a 302 redirect back to Shutterfly plus an access token. Her browser follows the redirect and returns to Shutterfly with that access token. And Shutterfly then uses the access token when it calls Facebook's APIs, and that token gives them access to the data that she shared. Now, OAuth does not specify a format for access tokens, so their contents can vary between implementations. So a common approach is to use a JSON Web Token, but there's no guarantee that any specific server will use any specific format. Therefore, since OAuth does not standardize the format of an access token, clients cannot make assumptions about its format or extract data from that token. The token is just a black box. Shutterfly can send it to Facebook to get data, but it can't get any information from the token itself. And that point is really important. It means that OAuth is not an authentication protocol, and it should not be used as one. OAuth allows Shutterfly to access Alice's Facebook data. It does not allow Alice to authenticate to Shutterfly. And the reason is that authentication is all about establishing the identity that's making a request. But that token doesn't tell Shutterfly anything about user identity. Shutterfly doesn't know who authorized the token, how the authorization was conducted, or even if the token was meant for Shutterfly or some other service. All it knows is it has a token it can use to call an API. Without additional information about the identity of the user, Shutterfly cannot use that token to grant the user access to Alice's Shutterfly account. And that brings us to OpenID Connect, which addresses that limitation. So OpenID Connect is an authentication protocol, and it's built on top of OAuth 2.0. It adds additional tokens using standardized formats, so the client is allowed to extract data from the token. And those tokens provide additional claims that identify the user that authorized the token, how the authorization occurred, and which client or service the token was meant for. With that additional information, Shutterfly can it can link the request to Alice's account and authenticate that user as Alice. So quick recap. JSON Web Tokens are a format for securely transmitting verifiable claims between two parties and are sometimes used for intra-organization single sign-on. OAuth is an authorization protocol that allows one app to access a user's data from a different app. OpenID Connect extends OAuth and adds identity layer so that it can be used for authentication. It's often used for single sign-on in consumer-facing systems. And SAML is conceptually similar to OpenID Connect, but it supports way more complex scenarios. And it's often used for single sign-on in the enterprise. So here's our progress so far. We've covered how to authenticate with credentials, how to use signed claims to represent identity between different systems, and how to use OAuth for authorization across system boundaries. Everything we've talked about so far has relied on something you know as the basis for authentication. So to wrap up, I want to talk about something about relying on something you have instead of something you know. So everything we've covered so far has some sort of vulnerability or weakness. Passwords can be reused between websites, and they're often written on a sticky note on someone's monitor. API keys can be stolen or captured in transit. Web tokens are vulnerable to replay attacks, and so on. Passkeys avoid those limitations by storing the authentication keys on the user's device. That means a single database breach can't expose them all to theft. They are also implemented in a way that makes them resistant to phishing and replay attacks. And here's how it works. A passkey is basically a public-private key pair like we saw earlier. Remember that a message signed with the private key can be verified with the public key. So when Alice sets up a passkey with a website, her device generates the key pair, and it stores the private key on her device. The public key is then given to the website that she's trying to log into. So when she logs in, the server responds with a challenge containing something called a nonce. And a nonce is just a random number used once. It's a random string the server created and sent over to her. Her device signs that challenge with her private key and then sends the signed value back to the server. The server can then use its copy of her public key to verify that signature. If it verifies, then it knows the client has access to her private key, and that's considered proof of authentication. In some ways, this is the opposite of how SAML works, because in SAML, the identity provider has the private key, and it's the one signing assertions. With passkeys, the client has the private key. It's signing a challenge. The server is then verifying. This improves security in a few ways. So passkeys are inherently phishing resistant because each key is bound to a specific website. Even if you manage to steal my Google passkey, you can't use it to access my Facebook account. And second, passkeys are resistant to replay attacks because each authentication attempt uses a unique and random challenge string. So replaying the exact traffic you sniff off the network isn't going to log you back in. And lastly, if an attacker does steal Alice's public key from that website, they can't use it to impersonate her. All they can do is verify a message she signs with it. Now, if an attacker managed to steal her device, they could try to extract her private keys from the device itself. So to reduce that risk, modern devices store the cryptographic keys in dedicated hardware that protects them with a PIN or a biometric identifier. So simply having the device isn't enough. There's typically some other authentication factor used to protect the keys stored on the device. On a desktop computer, that dedicated hardware is called a Trusted Platform Module, or a TPM. And that TPM is a dedicated chip. It's physically separate from the primary CPU and memory, and that separation helps keep those keys protected against malicious software running on the computer. This is actually one reason that Windows 11 can't run on older PCs. It uses a TPM for a lot of its internal key generation, so older PCs don't have the hardware they need to support that. Now, modern phones have similar hardware. It's not the exact same. And on Android, it's called the Trusted Execution Environment. On Apple, it's the Secure Enclave. The implementation details are different, but they all serve the same purpose of securely storing credentials on a piece of hardware. And you can also store passkeys on a physical device, like a USB security key. Now, to make it easier for developers to deal with all that different hardware, the industry has developed a standard API called Client to Authenticator Protocol, or CTAP. Browsers can use that API to obtain cryptographic keys from any device that uses that standard. Now, once the browser has the key, it can use another standard API called Webauthn to use that key to authenticate to a website. So these standards are related, but they're completely separate from each other. CTAP abstracts away interaction with hardware. Webauthn abstracts the usage of using those keys for authentication. So to simplify and promote passwordless authentication, there's a third standard called FIDO2. And it kind of combines both those two things into one overarching standard that provides a seamless interaction between the web, the browser, and the secure hardware. So when people say passwordless, they're generally referring to the complete experience provided by FIDO2. If you want to learn more about this, search for the protocol names. Don't just search for passwordless. You'll find much better information. Quick word of warning, passkeys are not a silver bullet. They have a lot of benefits, but if you support a fallback mechanism, like a password or some other way to log in if you lose your passkey, you're really only as secure as your weakest authentication option. So here's the last 45 minutes in a single slide for your screenshotting pleasure. Top right is a link to these slides on GitHub. Has all of my notes in there, so you can get everything that I've said if you want to refer to it later. And at the bottom is my contact information in case you want to reach out. I think we're right at time, so I will take maybe a minute or two for questions. Otherwise, I'll be on the Discord if you want to ask them in there. Thank you for your time, and enjoy the rest of Star Trek.
Shout them out, and then we'll have the speaker repeat them out loud so everyone can know.
Yeah.
Passkeys, is that specific to a device? So if you like log in from a phone versus a laptop, you have to create two different accounts separately?
Question is a passkey unique to a device? Yes. This is kind of one of the pain points about it. It can be hard to manage keys between different devices. But yeah, I have a passkey on my desktop computer. I have a passkey on my phone. That's where those USB keys can come in handy because you can use those in multiple places. But yeah, managing them can be a little bit of a pain still. All right, well, jump on Discord if you have any questions, and I'll answer them there. Thanks for your time.